Session of the workshop. We have two speakers that will be speaking, Prof. Plemmons from Wake Forest and Jeff Calder from University of Minnesota on two different topics, but I think they'll both be a very nice way to send off this workshop. Very exciting topics from Bob's topic on sparse recovery algorithms, 3D imaging, and then with Jeff will be talking to us about semi-supervised learning and mathematical foundations of that using PDEs to describe class of learning algorithms for semi-supervised learning. So, Bob?
Thank you. Thanks to you for the introduction, and also to the organizers, and for those of you who came to the last session. I'll start out with the co-authors here. A couple of words about that. Raymond, of course, spoke in the second session this morning. Sudhakar Prasad is currently at the University of New Mexico, and he works in quantum optics. So all of this is going to be optical imaging. Chao Wang is a PhD student of Raymond, and he spent the summer working with me on a J-1 visa funded by the U.S. Air Force Office of Scientific Research, as is Sudhakar Prasad and myself, working on the topic of what I'm going to speak about. And it's optical imaging, basically similar to what Raymond discussed this morning. And I've already mentioned some of us have funding from the AFOSR. Raymond has funding from the Hong Kong government, various research projects, including one that involves this optical imaging in super resolution. Okay, this is just a little teaser slide that shows what we're doing, what we're going to be talking about. That's some tests with a what's called a continuous exact L0 sparse recovery algorithm, and we'll be talking about that. This is an actual placement of point sources imaged by rotating PSF. So you make the PSF rotate and give range information. That's what the imaging system collects, and this is what this CELO algorithm does with, I believe, 15 point sources. It does have one false positive here. Okay, so we're going to see how we can set this up as we go along. A quick outline, some background information, some applications. Raymond talked about some astronomical imaging from the ground. We're not interested in imaging from the ground. Our imaging is space to space, tracking things like space debris, and also small satellites. Small satellites are put up there for various purposes. That they're too small to resolve from the ground. And then single molecule localization and microscopy. And we get a concept of super resolution here that's rather different from what Raymond discussed. And then we'll need a little bit of optics and physics here about how to engineer or change the port spread function according to the purpose of your imaging system. And this comes under the category of integrated imaging, where you use a device to collect the data, having in mind not only your application, but the way in which you're going to do the reconstruction. So it's integrated imaging. Some people call it integrated optical systems. And the key thing is we're going to get depth from defocus. We want to get the position of molecules or the position point sources which might correspond to debris in space. And so that's the problem statement we'll go through. One of the algorithms that we will talk about is the CELO algorithm, and we'll also touch upon some others. And we'll look at both Gaussian and Poisson noise models. The Poisson noise case, as you know, can be rather difficult, but more and more common now. Detectors in imaging systems use a CMOS type system that avoids some of the Gaussian read noise. Most of the noise is photon associated. So Poisson noise is important. We have some examples and concluding remarks. Here are a couple of illustrations. This is an exact image of in single molecule localization in microscopy. This is just sort of an artist's representation of what the artist might think would be space junk. Actually, space junk also includes very tiny objects which can damage an asset in space, such as a satellite or a space station, quite a bit. We'll see more about these in a moment. In the space debris, this is another way of displaying it. Most of it occurs in the low Earth orbits, and a lot of reconnaissance satellites, in particular, some communication satellites, but most reconnaissance satellites that may be doing hyperspectral imaging, LiDAR imaging, etc. And we've seen applications of that earlier, I guess on Wednesday. The outer rings are not so heavily populated with space debris, but there is space debris there, and these are where the geosynchronous satellites or communication satellites go. And this is by the European Space Agency. And this is just another one. The U.S. Air Force is designated to keep track of space debris, and they do it through a subcontract to Lockheed Martin out of Florida, and they placed a collection of a large number of radars all across the globe to track space debris, and the radars, of course, looking up. And the system that the Air Force asked us to look at is how to do a combined radar optical system for improved tracking. And we're investigating whether it might work and set up some guidelines for doing it. And here's another picture, actual data again in microscopy, localization microscopy. The way it's done essentially is you have fluorospores. This is fluorescence microscopy. You have fluorospores that are placed in locations in the specimen. It's sort of like little lights here. They glow, and the idea is to image those and use that information, use certain information to get their three-dimensional location, which is important in a variety of biological purposes and other purposes, like looking at biological processes, cells and proteins, and you want very high resolution. The old resolution would be over here. The new resolution, which is only been developed in the last 5 years, sort of the turning point was 2014, is in here. And you can also, in fact, there's an illustration on the Cambridge University has a center for doing that as well, and they have a nice web page. I'll show you that in a few moments. The idea, you could make it more general. It's like placing tiny, say, Christmas lights on a tree and taking a single image of that and using those images, using those point sources. You image those, you get to a three-dimensional location, and you get a representation for the tree. And there's a nice illustration of that on the on the Cambridge website. You can find it just by Google high resolution imaging. So we're going to engineer or modify the point spread function to get 3D information from a single. Now, Raymond talked about multiple images, multiple frames, from a single 2D image. Okay, all of these ideas relate to that in order to get high-resolution images from a single image. And it's able to modify the camera optical system, so it's an integrated imaging system to enforce a change in the PSF, and the change is going to be rotating, where the amount of rotation determines the range of the object, knowing the focal plane of the imaging system. So it's the distance of the focal plane from the object plus the distance to the point source that's out of focus. The amount of rotation encodes the depth. And the optical process sometimes is discussed as tuning an optical crank for ranging. And I think all of you have had an elementary course way back in physics, or in undergraduate or maybe graduate school, know that you can make optical processes to beams of light to rotate. It's essentially the phase rotating, and this is going to be an integral part of that. Now this is how it might be set up. Now this is going to be an optical element here. It's based upon Fresnel type lenses, and it can be besides the physical optical element, you can also simulate this with a spatial light modulator, and so you've got an object out here. This might be space-to-space imaging. This is a typical form of a telescope. The primary mirror, the secondary mirror goes back to a center hole in this. This hole is not there now, but it should be. And then a bending of the mirror, passing the image through this optical phase mask, and then we're going to see that if there are 3 point sources, 3 pieces of debris that you're monitoring or tracking, you see they're rotated. The PSF might be rotated in different amounts, and that's going to tell you the range. And the flux that you collect, flux is the amount of energy put out by the point source when it's illuminated or it's a fluorescent, it's a self-emitting system. And this is a list of, primarily concerned with the top, a list of various applications for in single molecule localization. The localization means you find the 3-dimensional coordinates, and you can gather other information with that as well. In biology, cell imaging, folding, membrane behavior, chemistry, spectral diffusion, molecular distortions, a wide range of applications in chemistry that are non-medical related. Physics, structures of materials, quantum optics itself. In terms of structures of materials, there's you wouldn't think of a microscope being large, but there's one at the Chicago O'Hare Airport of one that's huge, and it images through a piece of metal that may be composite, looking for how the molecules of different materials are arranged. Also in physics, quantum optics is another example, and this is by some authors. Morner is a Nobel laureate. Well, I'll talk about that in a few moments when I'll get back to some of his work and some work of others. So we're going to have a Fresnel type lens. You may not you may not be familiar with those, but it's a typical type lens that smooths things out. It enables 3D localization. We have some algorithms to do the recovery of a good image of the point spread function, and uses some non-convex algorithms. We work, keep in mind that we work with a system that takes a single snapshot. Now, localization of molecules can be done by various methods. Astigmatism methods. They all use a process called localization by defocus or focus. And this does too, but it's a single snapshot. The other methods like storm or palm that are used, or astigmatism methods, require multiple images. But the system may be moving. The molecules, it may be a living specimen that you're imaging. And in the space situational awareness of space disturbance, certainly the objects are moving. So that's from defocus. So we want to get not only the x-y coordinates, but the z coordinates. We also want to measure the flux or the energy put out by the point source that you're imaging. This is a standard representation for defocus. I think you all know from just elementary physics that defocus is a quadratic aberration. It's a quadratic aberration, and you see you get circles as the system goes out of focus. That is, you're imaging something. Well, if it's in focus, it's a small dot, diffraction limited. We're not worrying about imaging through a medium that may blur the object. We're worried about focus here, or thinking about focus. That's focus counterclockwise, defocus clockwise. Well, that's not going to help us. It doesn't record the information that we'd like. But if we modify the point spread function appropriately, then the image of the point spread function, the point spread function you get by imaging a point source, can be made to rotate in different amounts. Either we call this a positive direction, this a negative direction. So we're going to see how to get a high resolution, three-dimensional image that's independent of, is not sensitive to low light levels, has various other advantages. And it's going to have a single lobe. By the lobe, I mean the way in which you can determine this is an elliptical shape. The lobe is pointing in that direction for that -8 radians. Here's some other types of phase mask that, other than the single lobe, that can enable PSF rotation. And no rotation here with a standard diffraction limited image. Here's a so-called double helix, named double helix by Professor Raphael Peterson at University of Colorado in the ECE department. You can create a dumbbell type. These are the structures of the optical elements here. No structure here. And you can have, say, 2 lobes or 3 lobes. The 2 references we're going to talk about, some work by Sudhakar Prasad, who's the overall project investigator of this, principal investigator, and Chao Wang. He's a student of Raymond at Chinese University of Hong Kong, and he is very bright, and he's made major contributions to this work so far. And Raymond and me and Sudhakar Prasad, optimization method for point source localization from PSF engineering. The paper is still in progress. Here's some earlier work by Raphael Peterson. They have a very good public relations staff at the University of Colorado. Also, Cambridge does with a group here that are doing something similar. This is sort of the idea of a two-lobe or a double helix, he calls it. He names it a double helix, rotating PSF. And this would be a standard PSF of images either in or out of focus. And this is sort of recovering the point source localization of, I guess, 5 point sources. Standard PSF, and this is with the double helix. You can see the image of the double helix here. And He is sort of the father of engineering the PSF for this purpose. You may have heard of cubic phase masks. Cubic phase mask, they have a cubic design, and that's where you modify the phase, as you do here, so as to dampen out the quadratic phase associated with the defocus. So you can extend the depth of focus for a camera from here, say, to up there. It has a lot of applications. The group called CDM Optics at University of Colorado Boulder developed that process, and we worked with it too on a grant from the intelligence agencies in the United States for iris recognition by the imaging the iris as certain patterns. In fact, that idea was developed here at Stanford, at Cambridge by John Dogman in the computer science department. He's still working here. And his picture, along with, you may have seen the National Geographic magazine issue that showed the Afghan girl and how she was identified. Her picture was taken maybe 10 years earlier, and how she was identified using iris recognition. And Dogman was a major contributor to that article in the National Geographic. So he's here at Cambridge. And there's some other people who've made major contributions to rotating PSFs, working with the double helix type. William Warner, he and two other people shared the Nobel Prize in chemistry in 2014 for high resolution or super resolution imaging and microscopy, with not just medical type applications, but with applications to physics, chemistry, and other areas. And his talk when he accepted the Nobel Prize was three-dimensional super resolution imaging of single molecules using a double helix point spread function. I forgot to mention when I had this one up, Raphael Pietson has a company. The cubic phase mask people had formed companies too, and they sell these phase masks and associated software for $30,000, and that's not Hong Kong dollars; it's U.S. dollars, so they're expensive to buy. A group at Rice University bought one of them, and they've done some work on this too. And I met with Christy Landis. She has a group at Rice, and went through what they're doing, and we're hoping to do quite a bit better. Their paper on this, recent paper on this, is generalized recovery algorithm for 3D super resolution microscopy using rotating point spread function. They bought one of Pieston's optical systems with the software. Okay, a little bit of imaging physics. This project, at least for three of us, is funded by the imaging physics program at the AFOSR. You work with the orbital angular momentum of beams of light. The beams of light can be made to rotate. And that's going to cause the image of the PSF to rotate. The PSF, of course, is determined by a point source, the image of a point source. And you can do that either with Gauss-Daguerre type beams or non-diffracting Bessel beams, which Sudhakar Prasad, who invented this process and patented it, chose to use for various reasons. You get a PS image rotation by a twisted wavefront phase. The wavefront phase is twisted, so the amount of rotation or the amount of twist gives you an indication, a good indication of the depth of the object you're imaging. Well, what we're going to do, it encodes the XY position. We're able to get the depth, which is the important thing here. It's not that difficult to get XY positions, but the depth is very difficult, very challenging, it's called. You can also get the flux, which is important in determining the mass of the point source. especially important both in biological applications and in space debris location. So the 3D information is encoded in the defocus 2D image. And this is just a little more of the optics that we're using. You saw this expression here when Raymond gave his presentation this morning. The point spread function is the absolute value squared of, this is the spatial point spread function, of the inverse Fourier transform of the pupil function of the imaging cab system, like a camera, times e to the I times the phase. Now this is the modified phase, modified relative to this function psi here, that makes the point spread function twist. And the zeta here is the defocus parameter, and from that we're going to get the L0, which is the distance of the focal plane here, L0, plus the delta z, and then you get a scaling factor out here. And so adding those two together, we get a representation for the zeta value, the distance of the defocus. So we get the image of the point spread function. How much it rotates is encoded into that zeta. Okay, and here's where you have 2 point sources, and so you get 2 rotating PSFs. It's a little bit hard to see that on the screen, but these are 2 point spread functions where the objects are in different z planes. In other words, this one is rotated more than this one, and actually in the counterclockwise direction. And we can form an overall PSF in this way, and it becomes apparent when when I show you the next slide. And right now we're assuming in the slides that we have Gaussian noise model. That simplifies things a lot, but in some cases, with some imaging systems, it's not going to be realistic. And then you can think of the overall point spread function as a 3-dimensional tensor. So the point spread function is 3-dimensional. Here, in this case, we have 4 point sources at different, this is on-axis point sources, at different distances from the camera. And this is how the point spread function looks when you generate it. And the A's of the point spread function, spatial point spread functions, associated with, say, zeta 1 up to zeta 4 in this case, and then the transpose of that. And here's the optical element that causes the PSF to rotate. And here we can order these PSFs, these 3-dimensional PSFs, accordingly, and represent the for a single object we get an overall PSF. And what Chao Wang did in setting up the model and doing the computations is he ordered it so that you're going to remove every point source, and you're going to start removing them from the one that has the highest flux, and so you order these so that happens from the bottom to the top. And we need to look at the 3D convolution of these 2 3-dimensional tensors. So it goes sort of like that. If you have 2 of them here and you image with the system, the point spread function of this convolved with this 2 point sources gives you 2 rotating PSFs in 3-dimensional space. Okay. How much they rotate? That one rotates a little more than this one. How much they rotate, and you can see the rotation here, Verity, determines the range of these objects. Obviously, that one's the z coordinate is larger than for this one. Okay, here's the forward model. So we're going to solve inverse problems, as almost all the talks here have done. And this is the 2-dimensional image, a snapshot image. Only one image is taken The T is tau is just an operator or a function that picks out the appropriate slice of the three-dimensional tensor that corresponds to a particular point source. And this is the unknown three-dimensional tensor. Remember what I showed you early in the talk of the rotating three-dimensional representation of the point sources that are recovered? And each slice is a rotating PSF image. And of course, X is the unknown. Here we're assuming the Gaussian noise model for simplicity. We'll look at Poisson a little later. This 3D convolution, and we need to use that in the computations. And tau is the operator I mentioned. Okay, the optimization model is going to be sparsity constrained. As you might expect, in looking at the molecules or the point sources in three-dimensional space, some of them can be very close together and can almost overlap. Sort of like in astronomy having a binary star, different distances apart, but the XY position, the translational image, is almost the same. And so we consider a swarm, what we call a swarm of point sources, like a swarm of space Debris tends to have a gravitational effect on it. It tends to cluster them into clusters that rotate through the orbits and the low Earth orbits. And so we want to find the locations and values of the point sources, and we're using sparse recovery. Optimization model is something like this. A usual, in the Gaussian noise case, you'd use a quadratic here, and a regularization parameter, and a regularization function here. And this sort of defines what I just said. So I'll move on from that. Now we're going to look first at, well, in fact, primarily at what's called the CELO algorithm. They call it, these authors, it's a fairly new method that goes back to 2015 and some publications this year. They call it a continuous exact L0. That doesn't mean they get exactly the global minimizer relative to the L0. Of course, in general, it's an NP hard problem. You can get a very good estimate though. If the model is quadratic, the fit to data term, and they have a follow-up applying it to high density molecule localization, but they're just working with two-dimensional applications here. We work with the three-dimensional, so they have to have multiple images to do this, using, say, the Palm algorithm or the Storm algorithm. There's an algorithm called Thunderstorm, which is a faster method for the storm system, which is very slow. And once again, it's a 2D application. But they've done a very good analysis of what they call the CELO method. And the CELO method can be described by this process here. This is the regularization function. Let's see, we got to have a typo. Well, there's going to be a lambda here, but a regularization parameter, which it's involved down here in the algorithm itself. This is rather similar to the method that Bang Ki Jin from University College of London discussed for L0 regularization, sparsity for sparse recovery. I guess that was on Wednesday morning, the last speech on Wednesday, the last lecture on Wednesday morning. This is very similar to it, but not quite the same. But they have similar properties. They're both sort of bound into the quadratic Gaussian model. But the CELO method has some additional properties to what he discussed. It turns out that the minimizers of the of the total L0 optimization problem is contained in those of the CELO method. And not only that, and so if you take a local minimizer of relative to CELO, then you can get a local minimizer from it for the original problem. And it turns out that that means that some local minimizers of the L0 problem are not critical points of CELO, which means that CELO can avoid some local minimizers, simplifies the computation above what Bing, Kai, Chen discussed. And how do you implement the CELO recovery algorithm? And this is what Wang and Sudhakar came up with. And it reduces to using an ADMM process, separating this functional here from that one into two parts. Everyone is familiar with ADMM, and each iterative step can be modeled in terms of an iterative, refined L1 process, similar to the L1 model. And a little bit of post-processing is almost always necessary for these types of problems, and you can do a Taylor's expansion to improve the algorithm, and you can also use a gradient descent method. Here's how it would go, this is just the first step, and then a gradient descent to improve the location. The pluses are the estimations, the blue dots there are the approximation. There are other algorithms for working with the L0 pseudo-norm as the regularization functional, orthogonal matching pursuit. This is a relatively good approach. Iterative hard thresholding, group sparse recovery via the L0, L2 penalty. Wang, Jin discussed that. Various other non-convex optimization algorithms that I don't have time to go into. Now, how about the Poisson noise case? In the Gaussian case, we're going to take this model and convert it to a Poisson model. And so we have the same representation here, and we're going to modify that. And this we need to add the background, and we're going to assume a constant background, which is true in our applications in microscopy as well as the applications in space situational awareness. And it's signal dependent. It's not additive. It turns out that the group at Stanford and also the group at Rice University made a mistake in their implementation of the Poisson model. They just did it in an additive way, which is theoretically not correct. And so I'm going to be running short of time, so I'm going to go through this fast. So the idea is to use a maximum likelihood distribution, and that's going to be equivalent to minimizing the Kullback-Leibler divergence associated with the fit to data term up here. It can be done in this way, and I believe this is out of a paper by Raymond. And so doing that, you get an L0 model that looks something like this. You want to minimize the L0 pseudo-norm such that the Kullback-Leibler divergence of this is less than epsilon. And so the regularization model looks something like this. And you can use different regularization functionals. You can actually use CELO here, as we just discussed. You can use the L1 functional or sparse recovery, or some approximations to it. And you can use ADMM to solve the regularization model, as you're all aware of. And so you get a U0 and a U1, separating the variables, and the process goes something like this. And the algorithm that's being used is an iteratively reweighted L1 algorithm. And minimization problem in each iterative step is similar to the L1 model. And so you can use ADMM. And we're going to look at some performance of both approaches. The L1 model approach using ADMM and the CELO approach. And this is the setup for the Gaussian noise case. And for the Gaussian noise case, we're going to compare that method with the CELO method. We use some representations for the CELO method, not the CELO, but for this algorithm, based on work by the group from Rice University. And we look at just a small number of points for illustration purposes. Chao Wang has actually looked at a emitter density that's very large. And noise level is 10% of the highest intensity. And the evaluation criteria is going to be a recall rate and a precision rate. Precision rate depends on the number of false positives that you have. Okay, you can see this with 5 point sources. Now these are the rotated PSF. This is the observed image in the presence of noise. You might wonder, well, why don't you use some sort of noise removal algorithm? Well, you can't afford to lose the information because these rotating PSFs have some lobes that have low flux out away from the elliptical shape. And so they both work are similar there. In this case, this one gets 2, 3 false positives. This only has 1, and the others match up exactly. And with 15 point sources, the L1 approach has, I guess, 5 false positives, and we only have 3 here. And this is a little table that looks at both the recall rate and the precision. And the recall rate, defined this way, the number of identified true positive emitters divided by the number of true emitters. That's the simulation stage. We know the number of true emitters. By the way, in practical applications, you don't know the number of point sources. Okay? But you can figure that out by your algorithm passing through and starting the one with the largest flux until the flux goes below a certain tolerance. And that's an area for learning methods, learning the tolerance for which you cut off the process. So you can see with the L1 ADD, the recall rate's about the same as with the CELO method, but with the precision here, number of identified true positive integers by the number of all emitters identified by the algorithm gives you a much higher precision than the L1 ADMM method. So CELO is very nice. It's very nice for the Gaussian model, the Gaussian model. So you're using a CCD type detector. They're more common than CMOS, but CMOS with the necessary Poisson noise model is gaining on that. So for the Poisson model, we're going to consider 3 density cases. Again, we randomly generate a collection of various distribution of the emitters, and the number of photons emitted by each point source. We need to know that to set up the Poisson distribution for the simulation. It has a mean of 200 photons, and we use B equals 5 for the fixed background, and recall and precision rate as the criteria. Now, this is what I've already told you is going to happen for the single lobe rotating PSF and the L2 data fitting term so that the Gaussian model is more appropriate. Then the two are similar in the recall, but the precision of the CLO is less here. And with the single lobe, with the Kullback-Leibler data construction, well, over here the recall rate is less for CLO. But here, with the non-quadratic or non-Gaussian model, the recall rate is greater and the precision is greater, slightly greater than that with the CLO. So the CLO method is really designed and has been analyzed for the Gaussian model, and that's this is what I'm saying here. The Kullback-Leibler data fitting term has better results than the L2 when using L1 regularization. And so we don't think the CLO is going to be suitable for the Poisson noise case. And any of the methods are going to have false positives, and it's difficult to identify the false positives. You've seen on the illustrations a moment ago, and some sort of learning process is appropriate here. The Rice people have made an attempt to do that. Okay, in summary, couple minutes left. We've looked at PSF rotation with a change of focus, enables target localization in 3D using a Fresnel type spiral phase math, and it's part of an AFOSR project, and we're imaging space debris as well as small satellites. A lot of interest in imaging small satellites from space-to-space telescopes. There's some danger in small satellites I don't want to mention. And 3D localization of space disturbance and space-to-space imaging by a laser illumination. And the Air Force Research Lab in Albuquerque is working on the laser illumination. It's associated with their directed energy, airborne directed energy project. Now, people call this, at least in microscopy, super resolution, the super resolution revolution. And there's actually a group here at Cambridge, and I guess centered in the chemical engineering department, has a web page that says the super resolution revolution. And it was the basis for the Nobel Prize Awards in 2014. Now, it turns out, just as a note, this became sort of a buzz phrase, super resolution revolution. In fact, there was a Saturday Night Live TV program. I don't know if you get that here in Britain or in Europe in general. Saturday Night Live put a little spin on this, where by resolution they were thinking of New Year's resolution. So resolution, not what we have here that we're talking about, and all of you are familiar with. It's the resolution, New Year's revolution. They had a characterization of super New Year's resolution, called it a revolution. Work in progress. We're going to be doing some comparisons with the double helix, which is a commercially available system. And there are a couple of reasons why we think the single lobe has a good possibility of being better. There's more clutter when you have the double helix in say in a very dense emitter system, and the Z location suffers in the which is primarily what we're interested in, the Z location, because the rate of the rotation is only half as much with the double helix as it is for the single lobe. Okay, another thing we're looking at is downsampling to speed up the computations. It has other advantages too. There are advantages of downsampling. Considering extended objects, we so far just talked about point sources, but like putting the Christmas tree lights on a tree and imaging that, we can get an extended object representation of the tree. So it's interesting to look at extended objects. And also considering spectral imaging for extended object to get spectral information such as multispectral imaging, gives you material information. Okay, well, most of the recent speakers have put up some sort of image of their campus or city they work in. And this is Georgian architecture. That's a picture of an image of the chapel at Wake Forest University, where I'm located. These are the Blue Ridge Mountains in the distance. So it's only about 30 miles to the higher Blue Ridge Mountains. That's the Blue Ridge Parkway you may have heard of. And it uses Georgian architecture, named after King George here. Okay, thank you very much.
We have time for questions? Yes?
Yeah, I have two questions, quick questions. The first one is, you mentioned, you compared the results of the algorithms with multiplicative Poisson noise and or additive Gaussian noise.
Right.
But you can use, for instance, Anscombe transform, and it has been used in astronomy.
We're using fast Fourier transform to do this.
Because with Anscombe, you transform multiplicative Poisson
Right.
in kind of additive Gaussian. So if you do that, how have you done it to see the results or to compare? Or
Yeah, we'll do
Okay.
that. Yeah.
that was
Good
my first
idea.
question. And my second question is about confocal microscopy. Could you use the method you proposed in confocal microscopy, or it's or any type of microscopy, such as confocal microscopy or other type, or it is dedicated to a specific type of microscopy?
Different types of what?
Microscopy. Is it you can? Could you use it in confocal microscopy?
Yes, you can.
So it's general.
Yes, it does. Yes. Chao Wang has looked at that. Yes, Mila.
How many objects you have to detect in practice? In practical system, how many objects are to detect?
How many objects
How
are?
many molecules?
In the biological application,
Yeah.
there can be hundreds of molecules that you're imaging. In other applications, maybe not so many. But when you're looking at fluorescence microscopy, you can have a large number of molecules. But if you do, you can use the patch process to looking at the overall theme of the single molecules.
Single.
And there are some references where they do that. Of course, we haven't looked at that.
In case if there are some
They call it the emitter density. For some applications, for some biological applications, the emitter density can be fairly large.
There is some occlusion. For instance, an object is occluded by another one.
Well, that's one reason we think the single lobe would do better than the double helix. The double lobe is if the images of the rotated point spread functions are very close together. So, like if you have a binary star situation, then that complicates the recovery process. So, if the emitter density is great, that complicates it, and that will complicate it for any algorithm that we've seen so far for this process.
Do you have the possibility to have a view from a slightly different angle?
Well, one way it complicates it, if you remove a point source after computing its location and remove that PSF, you may take part of the other PSF if it's very close to it. And so there's some process of setting tolerances to avoid that.
You use regularization for, I think, the L0 and 1 norm for the amount of events to some extent. But you also showed that you have the helix that you actually want to identify, right?
Yeah.
So is it have you tried to actually regularize these lifted geometry as well? So if you think about rotor translation,
No, we've not, but that's a good point.
so I'm thinking about you mentioned at the end that you want to have compressed sensing or something a bit more, let's say, faster computation. Yeah. So in some way it will always lack in the actual geometry of that helix, right?
Yes, that's right.
But there's no.
We
no
haven't looked at that. That's a good point.
A short question, and that was the last point on your slide on multispectral, the sort of multispectral imaging aspect. So if you look at low photon count type of detectors in the multispectral domain, where you're performing spectral integration over say a 256 channel multispectral imager, then the statistics of a low photon regime are no longer Poisson,
That's
they're
right.
compound
That's right.
Poisson.
Yeah.
So
That's very difficult.
yeah,
Yeah.
I would assume you could implement similar types of Kullback-Leibler regularization approaches
Yeah, I
in
think
that
it would be
case too.
different. Yeah, it
Yeah.
would be different. This is a difficult process with the spectral imaging.
Yes.
We've done some of that with looking up from the ground at satellites, where you have a small satellite, say that it's unresolvable, and you only get one pixel, a single pixel. But if you do a hyperspectral image of that pixel, you can determine the components of that satellite, and by a certain process using NASA information, you can determine what type of satellite it is, what function it is. The solar panels or the communication wires are made up of copper, silver, gold, etc. So with a single pixel, you can glean a tremendous amount of information using a hyperspectral image.
Yeah,
Yeah.
but then you're in the so-called FOC
Yeah.
limit, which implies that you no longer have Poisson statistics.
That's it.
They're compound.
But there's in place imaging systems at the Air Force facility in Maui, Hawaii, on Mount Alaaka that does hyperspectral imaging.
Yeah. I'm not sure they use low photon
Yeah.
algorithms. But
Yeah, they do.
They do. Okay.
Yeah.
Great.
Okay.
Thank you.